All right, so we're looking at chapter 8.1 in the book, which starts on page 498. We're looking at inverse variation today. Now what we're going to do is we're going to take a look back at direct variation, which is something that you did starting in Algebra 1. Direct variation has a formula associated with it, which is y equals kx. Now we can also change y equals kx to be k equals y over x as well, and that helps us to determine if we have direct variation relationships between ordered pairs. The new one that we're going to look at today is inverse variation. So inverse variation, the formula for that is y equals k over x. Now what we can do is we can change this around a little bit. We can move the x out of the denominator, move it to the other side, and we get k equals xy. Again, by having k equals xy, we can also check a little bit easier, more easily to see if we have inverse variation. So we're going to look at problem number 1. In problem number 1, we're given this set of points in an XY chart. So we've got 2, 15, 4, 7.5, 10, 3, and 15, 2. The first thing I'm going to check is to see if we've got direct variation. Now, direct variation, again, is simply going to be y divided by x, and if every single result is the same, then that means it is a direct variation. So if we do 15 divided by 2, we're going to get 15 over 2. If we do 7.5 divided by 4, well, the thing I've got to do with this, I want to get rid of the 7.5. I want to get rid of the half. So I'm going to multiply the 7.5 by 2. That gives me 15. But when I multiply the 4 by 2, that gives me 8. So I get 15 over 8. So 15 over 2, 15 over 8, they're not the same thing. This is not a direct variation. So now I'm going to check to see if we have an inverse relationship. To do the inverse relationship, do x times y. So 2 times 15 is 30. 4 times 7.5 is 30. 10 times 3 is 30. And 15 times 2 is 30. Since 30 came up every single time, then that means that this chart does demonstrate an inverse relationship amongst the two variables. Now what we're going to do next is take a look at problem number B. And in this one, it says a plot of points suggests that an inverse relationship is possible. Test to see whether the products of x and y are constant. So in this case, we're going to be given a new xy chart, and this time we've got 2 and 10, and we've got 4 and 8, 10 and 3, and 15 and 1.5. So what it wants us to do is test and see if this is an inverse variation, or if this has an inverse relationship. So we're not going to worry about y over x, we're only going to move on to x times y. 2 times 10, 20, 4 times 8, 32. You can stop right there because we can see that the k value is not the same, which means that we are not going to have an inverse relationship for problem number 1b. Go ahead and take a look at got it number 1, work those out on your own, and then check the answers that have been provided to you. Okay, in problem number 2, we're going to be told that x and y vary inversely. Anytime that you see this, you automatically think y equals k over x. So go ahead and write this in, y equals k over x. So again, anytime you see x and y vary inversely, automatically go straight to the formula. So what we're going to do is we're going to take the values that we've been given, x equals 4 and y equals 12, and we're going to plug those into our formula here. So we're going to plug in 12 for y, and we're going to substitute 4 for x. So we get 12 equals k over 4. Now you've got to think to yourself, how are we going to be able to isolate k? Since k is being divided by 4, we want to multiply it by 4. So we multiply both sides by 4, and you're going to be left with k is equal to 48. Now we've been asked, what is the function that models this inverse variation? So now that we know that k is equal to 48, we're just going to take that and we're going to plug it back in to the inverse variation formula. So y equals 48 over x is going to be our solution for that problem. In B, we're given what does the graph of this function look like. So make a table of values and sketch a graph. So you're given 3, 16, 4, 12, 6, 8, 8, 6, 12, 4, and 16, 3. What you can do is you can sketch those onto a coordinate plane, and you're going to see that you end up getting a graph that looks like that. So the inverse variation looks a lot like an exponential graph. Then in C, we're asked, what is y when x equals 10? So we're going to go back over here to this. We now have what our inverse variation looks like, the function for it. Now we want to find out what is the value of y when x is equal to 10. So we know that x is equal to 10, so we're simply going to substitute that 10 in for x. So y equals 48 over 10. What goes into both 48 and 10? We have 2, so 24 over 5, or 48 divided by 10 is 4.8. And that's how you do problem number 2. Go ahead and take a look at got it number 2 in your book. Work it out, see if you can work it out for yourself, and then check the answers that have been provided to you. Okay, in problem number 3, we're going to take a look at a situation where we're going to model inverse variation. And what we're given is this table that tells us the number of students that we've got working on a cleanup project and the time that it takes them to complete that cleanup project. So what we want to do is we want to end up figuring out how long or how many students are we going to need if we want this project, this cleanup project, to take 30 minutes. So the first thing we need to do is determine if there's any direct variation or inverse variation. Since we're doing inverse variation, let's do that. 3 times 85, 255. 5 times 51, 255. 12 times 21, approximately 255. And 17 times 15, 255. So what we see is that k is around 255. So every time that we do this, we can see that there's a relationship between the number of students and the amount of time that it takes. So how do we actually model this? Well, we know that we can either do y equals k over x, or we can do k equals xy. So we know that the number of students that we have times the time that it takes is equal to 255. So this is your answer for part A. That's the model that we've got, or the function that we've created. Now the second part of this is to determine how many students do we need if we want to finish the project in 30 minutes. So what we're going to do is replace t with 30. So we've got n times 30 equals 255. Divide out that 30. So n is going to be approximate, or is going to be 8.5. So it's going to take 8.5 students. We're going to round that to 9. It'll take 9 students about 30 minutes to be able to finish this project. So go ahead and take a look at got it number 3. See if you can do the problem on your own, and then check your answer against the one that's been provided to you. Okay, before we move on to problem number 4, we're going to take a look at a couple more formulas that you're going to need. If we do joint variation just means that we're going to be multiplying more than one thing together. So that's going to be z equals k times xy. If we get joint and inverse variation, then it's going to resemble something like z equals kxy over w. So the joint is going to be in the numerator, and the inverse is going to be in the denominator. Then if we have direct and inverse, our direct variation kx is going to be in the numerator, and our inverse variation y is going to be in the denominator. So that brings us to problem number 4, which is a word problem. What we're trying to do is we're trying to figure out how many bags of seed are we going to need in order to completely seed an area of a yard. And the information that we're given is that bags of seed in varies directly with the area A of the yard and inversely with the weight W of the bags. So we have both direct variation and we have inverse variation. So it's going to look like this down here. So we're going to start with the bags of seed N. So N equals, and then we always need our constant of variation no matter what we're doing. So N equals K, and then K is going to be multiplied against A because this varies directly with. So N equals Ka, and then the next thing that we've got is that this varies inversely with the weight of the bags. So we get N equals Ka over W. Now what we want to find out is how many bags of seed will we need to do a 9,000 square foot yard. So if 2 3-pound bags of seed gives us 3,600 feet squared, how many 3-pound bags are going to seed 9,000 square feet? So we're going to start with, again, N equals K, and we're going to fill in this A. So we know that the area is 3,600 square feet. Then over top of that is the weight of the bag. So these were 3-pound bags. So we end up with this here. And the number of bags of seed was 2. So now we're going to get 2 equals K times 1,200. And so K is going to equal 1 over 600. The next thing that we're going to do is we're going to take this K value and we're going to plug it in with these values here. The 3-pound bag, how many 3-pound bags of seed will you need to do 9,000 feet? So N is the variable we're looking for here. We're going to do 1 over 600 times 9,000 square feet over, then the weight of the bags again is 3. Now there's a couple of different ways you could do this. I'm going to go ahead and do 9,000 over 600, so we'll do 9,000 over 600, and then all of that's going to be divided by 3. So go ahead and take off 2 zeros each. So how many times does 6 go into 90? 6 is going to go into 90 15 times. So we get 15 over 3, which gives us 5. We're going to need 5 bags in order to seed 9,000 square feet. So go ahead and take a look at guide number 4. See if you can do that on your own. Check your answers against the ones that have been provided.